when we were sort of pulling this all together, we were sort of, you know, trying to find what people wanted to know about, and one of the requests was for, you know, what about existing systems, and what are the considerations for that. So that sort of led to us sort of going back to sort of the basics and speaking about those. And you know, there'll be people in here that know all this, and others that are less familiar. So it's good to go back to that. And so what we're mostly talking about are hot water systems, standard hot water systems. But the process really is the same when you're looking at these considerations if you were dealing with a steam system, but you know, the actual solution is a bit more complex for steam than it would be for hot water. So for most parts I'll actually just be talking about the boiler house. They're the three main components: the delivery options and your fuel storage. And those, you know, if you break it down, these are your three parts to it. You've got your boiler plant solution, and that does whatever it does in its process. You've got to store the fuel somewhere, and you've got to get that fuel into the boiler plant, and the fuel itself has to come on site from somewhere, and this part of it is you know, really an important part. So when you're sort of looking at these sort of for the first time and looking at retrofitting it into an existing plant house, you actually have to start at the back end, and you start back at your boiler, and that sort of really determines what happens going back through this way. So and so one of the first things we need to do is we make sure that our boiler is correctly sized. A large number of boilers are oversized. They're oversized for future production. That never comes. You know, processes on site may change. Lines of manufacturing may disappear. Poor design, risk aversity, and safety factors that can be built in, and so yeah, so it's sort of it does happen, and every plant, I've been to a lot of plant where I've seen it oversized by quite a lot. So we need to, first thing we need to do is estimate our load profile for our boiler. And this is just a photo off the internet of a heat meter, and heat meter is an accurate way of doing that, and we can also do it off fuel consumption, but it isn't as accurate for doing it on fuel consumption. So here's an example of this is a 4 megawatt VCOS boiler up in Dunedin. And we ran it for 10 days, this processing, and this went through one of their batches. They had a 10-day batch process, and what we saw was, you know, we only ever got up to about 2.7 megawatts, so they had a lot of spare capacity in that boiler. So really useful information when we're sizing these systems. One thing that you need to think about if you're going to go down this road of heat metering is making sure you do it during your peak period. You don't want to be measuring a summer heat load when your peak demand's in winter. Sounds pretty obvious, but yeah, you want to make sure you're doing that. So from a perspective of anyone here today that might be looking to switch and having some, you know, what is our boiler doing, this is the perfect time to be doing that monitoring and collecting that information for your system. This is another example of a large boiler that was oversized. These are older Tamac boilers. They're probably 25 years old. Each one of them, there's actually 3 of them. You can sort of see the edge of the bottom, the third one here. They are each 1.2 megawatts, and we did some monitoring on that, and the final solution was 2 new 750 kilowatt boilers. So just over 1 boiler was sufficient for their load, and yeah, we're not sure why they had so much capacity there, but it certainly was. We didn't need to replace it with 3.6 megawatts of heat, and now they've got 1.5 megawatts, and that seems to be more than meeting their requirements. Okay, so once we've established what our correct boiler size that we need, and we've allowed for our heat metering and done the analysis on that, we can then sort of work backwards and think about fuel storage. You know, how much fuel storage do you need on site? Again, as part of your analysis, with your load analysis, that will help you determine how much energy you're using per week, how much energy, you know, per day, per month. You also need to allow for some weather interruptions. The recent flood in Dunedin, snow, all of those sort of considerations, and vehicle delivery capacities as well. So, you know, I guess there's a balance between how big can you get a truck in there, what size vehicle can you get in there to get the cheapest price, your cheapest bulk price, versus how much do you actually need to store on site. So a sort of a rule of thumb of 5 to 10 days on-site storage. Now another way of doing the storage as well, which haven't got on the slideshow, is a just in time, but that's more a really large user site where you might bring in whole logs and have them sitting on site, and for those large users, you know, you might have 9 truck and trailer units turning up a day. So to reduce that, you could bring in whole logs, store them on site, and actually chip on site. So that means you need a lot smaller storage area because you're chipping just in time. But again, that's more the bigger guys that we're talking about with that. Yeah, so then we also need to look at what sort of vehicles, what sort of trucks have we got around. Have we got chip liners? You know, they need certain turning requirements. Are we in a public area? Or do we need to go into that next level of vehicle size in the 30 to 40 cubic range? The V-bin trucks, the moving floor trucks. There's a large number of standard trucks out there, some with moving floors that will just push the wood chips off, and there's also some purpose-built trucks around. And here's some early examples. There's your typical chip liner there with your 80 to 100 cubes. In Dunedin, Energy for Industry have built a purpose-built truck, and it's got the V-bin, the V sides on it, and going right down that middle is a big conveyor belt. And what they can do is actually extend out the back. At this back end, they can extend the conveyor out about 4 or 5 meters, and so they can deliver into some quite tight sites and control the speed of delivery. So that's a purpose-built truck. This is one of their earlier trucks, which is just a standard truck. So yeah, and with that comes site access, and what we need to think about with that. So a couple of sites around. Now this is where they had to make some modifications to the system, to their building site, to get the truck in and be able to turn around. Factoring those costs into there. And here is another site this is actually a delivery hole where the fuel goes in. Now that V-bin truck fits in there perfectly, and with the extension arm it can drive its extension arm straight into there, control the feed, and there's an auger system inside here, and they can match that auger system feed, and I think the delivery time into there is about 10 to 15 minutes to deliver 30-40 cubes into that site. So those are those little factors that you need to think about in terms of how long will somebody be on site. Are they going to be there for 5 minutes, or are you happy for them to be there for 25 minutes? This was just off a case study in the US where they'd sort of designed out for larger big trucks on where you might put the chip receptor versus having it around the corner there in terms of making access for large chip liners, and the thought that went into that. So planning is essential for delivering these larger 100 cubic metre volumes, because you don't want them on site for a long time. You want them to tip and go, and you want that to be over in about 5 minutes. Coal boilers are a perfect setup for wood chip. Naturally, they've got the delivery system, they've got the augers, and they've got the large space for taking these sort of deliveries, so they convert really well in terms of an existing site. Going from coal to wood chip, you're going to need larger volumes, so you need to start thinking about maybe increasing your bunker storage, and how, as part of that analysis, that bunker size will determine how big that storage needs to be, and in some cases what they do is they'll just block this up and put a little trough in front of it. So this is another system on wood pellets, and that's running Tamak boilers, and they've made some modifications in the boiler here. They were just steel plates that they put in to help the material flow a bit better, and they didn't need to make any modifications other than putting in the side beam to stop the truck going back too far, but the volumes were sufficient to maintain that. That wouldn't be the case in a wood chip situation. You'd need to look at increasing that volume. We've got above ground options for conveying the chip. I mean, this is real simple. The truck pulls up, he dumps, he's gone in a couple of minutes, and he's on to the next site. From a supplier's perspective, that's very attractive. Look, this site's a great site as well. It's just a matter of opening the doors and the truck comes in, and I think that's about another 5 to 10 minutes delivery time for 30 to 40 cubes into this site, and it's conveyed up and dropped into the storage bunker. And the boilers are over here. This is the University of Otago site, and what's fascinating me now is, now that wood chip is becoming a lot more common in Dunedin anyway, people are starting to have a bit of fun with it, and so what they're trying to do here is they're taking heat out of their boiler house, and that is a air ducted system, and in the four corners of their boiler house they're dropping the air down. Is this right, Mark?
Yep.
And letting it come up, so they're trying to preheat, they're preheating, drying their wood chip. So you're paying for this chip when it turns up at the door, and it might have 12 gigajoules in it per tonne, but by the time they dry it, it might have 15 gigajoules in it. So they're getting some free energy out of waste heat in their process. So that's really interesting, and that's I guess that's the start of us starting to experiment and try new things as we become more familiar with wood energy. Here's a couple of other examples of trough systems where they're delivering into a trough. Yeah, they had real troubles with this side at the start, and they had troubles with trying to control the flow of chip into the trough to match what was going out into the boiler house. So they developed a sort of bag around the end that stopped this from flying open, obviously, and then they had controlled the flow by the angle of the truck. They moved on from that truck onto another truck, but that side again, that was about 15 minutes to deliver 30 to 40 cubes, but they had real control issues with delivering into that system. And I think they also there were dust problems, and that bag helped get around that dust problem. So when you're thinking about these storage bunkers, you know, thought into auger jamming, maintaining the sweeper arm on a lot of these systems. They'll have there'll be an auger that goes up from here, that goes up the wall inside. Now in this case here, they've got an entrance at the top, and you can access the auger for there. And the other unthought about part of it is inside this bunker is a big sweeping arm. Now that sweeping arm collects the wood chip and collects it over, and it pushes it into the auger, and then that auger travels and conveys that chip into the boiler. Some plant, there's actually a mechanism that sits at the base that converts that sweeping arm motion into the auger, and you know that needs maintenance. Doesn't need a lot of maintenance, but it does need some maintenance. So how do you access that? A lot of sites will put in we'll just put the auger in and the sweeping arm in, and fix it to the floor, and then they'll normally fill that void with just wood chip. So to get at that, you need to actually get that system empty, and you might have to run the boiler in summer for a few hours or a few days to get rid of that chip, or plan it well, or you could build a floor that you might be able to get in under. You know, I don't know, but just considerations for that. What I really like about this side here is you've got your access to the top. You know, there is an auger in here going up the inside of the wall, and you can get access to it. The other part is if you do have a problem, how do you have to get in there and you have to clear out the chip. So you know they've got an area for having to do that if they need to get in there and clean it out, suck it out, and also ventilation. They've got ventilation inside, and stops that build up of condensation inside the bunker area. And in this particular site, they've actually got another sight glass inside, another sight window where you could access through that point as well. So, you know, a good example of sort of planning for maintenance and future potential issues. I think most of us have seen this chart. It's an ECA chart. This isn't the latest one. This is 2009, but it hasn't changed too much. Yeah, look, here's the business case for wood chip is really down this end of the spectrum. I think this diesel price has come up a little bit. This is where our low-hanging fruit is in conversion, so electricity, diesel and LPG boilers, so that the business case against these stacks up basically in that margin between what you're going to save. So sites where you've got large LPG boilers, you know, they stack up really quickly. And of course what it's also showing is coal. So just on a financial straight financial dollars per gigajoule basis, yeah, it's a hard sell to coal users. You know, you can see doubling, tripling of your energy expenditure by switching to wood chip. So yeah, so the business case is really in this end of the spectrum. Look, wood boilers are as reliable as fossil fuel boilers, and if you are in those LPG or diesel boiler systems, then you may want to consider retaining that boiler plant. You know, if you do have supply issues, or if in maintenance, then you've got a backup boiler there. If it's a good operating plant, then you know, it'd be silly not to throw it out. And in terms of size, you know, I mean, Splash Palace is a good example. They've got a large room, and it's taken up all by a wood boiler, and in the corner they've managed to squeeze in their diesel boiler. The College of Ed is also another site where they've also managed to save their boiler and put it in on the side and keep it. So, you know, I can't see why you wouldn't want to keep it as a backup for those reasons. You know, can you use that same boiler for peak loading? You know, I think it all comes down to what your load profile is. You know, this system here, you probably wouldn't. You'd probably design this system for, you know, a 2.5 megawatt wood boiler. But this one here, if your load profile is quite up and down and quite jumpy, then you may want to consider, can I use that diesel LPG boiler for taking on that peak, and I design a base load boiler for my a base load wood boiler for getting that base load. So you're not going to get all of the energy, but you'll get the 70–80% of it. So that comes down to the business case and working out, you know, the cost of plant, the running costs, and the capex of the two systems and the merging. So accumulators, now look, they're commonly used. They improve boiler cycling. Now the cycling is when the boiler's turning on and off all the time. If we have a sort of a lumpy load like that, you know, the boiler's going to get up to temperature, turn off, it's going to need to turn on again. So to get around that, we put in accumulators, and they allow for a longer continuous operation of a boiler, which, you know, boilers like to run it at higher efficiency, at their highest load. So and I don't know, Christian, have you got a rule of thumb for litres of water per kilowatt of demand? Has you got anything like that? I know in solar they do 10 litres per kilowatt, and so but they come in all shapes and sizes. They're, you know, from 10,000 litres. So a 10,000 litre tank at 40 degrees delta T will hold 500 kilowatts in it. So you've got a 500 kilowatts for 1 hour sort of battery that you can use. And finally, but not least, is energy efficiency. I guess that should have gone up the front as well when you're looking at your demand profile. You know, where can you reduce demand on site? Are there heat recovery opportunities through your compressors, your chillers, your refrigeration system, gas heat recovery, and also, I guess, sort of going out beyond the boundary of your business. You know, what are other organisations around you doing? Do they have a waste heat stream that you might want to utilise? A great example is down here is McCullum's. They've got water for Africa, so if there was a site next door to them, maybe they could utilise that. So it's sort of thinking a little bit outside the square, and the collaboration around the energy efficiency side of your plant, so that you can reduce your demand